Hi, welcome to the Stinty definition number 3, discrete versus continuous systems. In this video, I'll explain the difference between a discrete and a continuous system, how to identify such systems, and why this is important to us. The purpose of these definition videos is that they're foundational to a lot of the work going on at distinty.com. This definition is used in the rules of acquisition, and it's also used to support the electrogravity work. And you'll find out a little later where it's going to be used. Now, the definitions, instead of me having to, every piece of work where I need this definition of having to re-include it every time, I'm going to reference these videos from the other works. And you'll be able to go find these by going to the distinty.com website. On the main page, there'll be a specific link to click on to get to the definitions. It's a lot easier for me to do it that way than to put these little things in the YouTube videos. YouTube's a little awkward for putting stuff in. It's too slow. Before continuing, I would like you to review the definition number 1, emd003, on determinate and indeterminate systems. Now, what's a discrete system? Well, a discrete system is composed of corpuscular components. Just like this little thing of Legos here is made up of discrete little blocks. And see how it's stepped? It's not a continuous slope. It's like a stepped slope. And so there's discrete steps in the shape of this block. Now, each one of these corpuscular components themselves can only exist in finite or limited states. In other words, how many squares are on the top, what color it is, what shape and what size. And so in other words, a discrete system is a system composed of smaller discrete components that only exist in a small variety of states and colors and shapes. An example of a discrete system is like a bitmap. In a bitmap is made up of pixels. Each pixel is a discrete pixel. That's why this looks stepped over here. Now we can give the illusion of a slope by dithering the color. So you see how it goes from black? See how it goes from black to gray before it goes to blue? So if you pull this far, far away, this gives the illusion that it's a nice continuous line, when in fact it is a stepped system. And each one of these pixels can only exist in a few select colors. Okay, so this is a discrete system. Also, an example of a discrete system is like computer memory. Okay, each memory can exist of one bit, and that bit can only either be in the 0 state or the 1 state. If it's in any other state, well, the computer is not functioning properly. And there's a note here that computers are discrete, causal, and deterministic systems. So if you reviewed the video on deterministic systems, you will understand what we mean by a deterministic system. Matter is composed of discrete corpuscular blobs called atoms, or even molecules at that level. And these blobs can arrange themselves in different states based on the energy level, but ultimately it comes back to that if I remove this one object from this system, it's removed no matter what the state of the system is. So it's a very discrete system. Okay, and if we look at hydrogen atoms, those hydrogen atoms the energy levels of the electron orbits can only exist in very discrete energy states, just like our Lego blocks that can only exist with certain number of nipples, whatever you want to call them, in discrete colors and discrete sizes. Here, the hydrogen atom, their electron states can only exist in certain discrete states and nowhere else. This is a discrete system. It's ironic that matter is composed of numerous objects that can only be in discrete states. This is very similar to the characteristics of computers, which are deterministic systems. Okay, and the irony is that in matter, we call these discrete energy states are called quanta, which means tiny amount. This is where quantum mechanics gets its name. And quantum mechanics is based on probability and statistics, which is typically what we use for an indeterminate system, is if you review that video. So we're using an indeterminate modeling system on a system that assumes discrete states, just like computers, which are deterministic systems. Now we're going to cover this more in the coup de grace video on quantum mechanics. We'll get to that. That's a later video. Just kind of giving you a little foreshadow of where all this stuff is going. So the properties of a discrete system is that it's divisible. In other words, I take this gold bar, I can cut it in half, and I still have gold, just two different pieces. And I cut it in half again and still have gold. Now, interestingly enough, this logic here is logic that was used by some philosopher in either ancient Rome or ancient Greece who basically theorized the existence of atoms long before they could know atoms. And it's actually an interesting story. I don't know all the details right now, but you can go look it up. But now you get to the point where you keep dividing your gold bar down to the point where you get down to a single gold atom. And let's assume we had a very magical knife that we could cut this gold atom in half. Well, because it's got an odd number of protons, we can't evenly divide it in half. So what we could do is with our magic knife is divide it, and you would end up with yttrium and zirconium, because that would equal that's where 79 protons can be divided into an object of 39 and 40. Because if we actually take the gold, right, so at this point, when we get down to dividing the gold atom, we no longer have gold. That's the point of this little slide here, is that there's a lower limit that if you keep dividing something down at a certain point, when you divide it in half, it's no longer what it was. It's now something else. So it ceases to exist at a lower level. Well, it ceases to exist as a gold, okay? So from this, we can put together all the properties of a discrete system. A discrete system is finite in size. It's divisible, but it's not infinitely divisible. It would cease to exist, in this case, as gold. And if you broke apart some Lego blocks and smashed them, well, they would probably no longer function as Lego blocks. Now, a continuous system. A continuous system is best described using fonts. If you ever took a bitmap font and blew it up, you would end up seeing all the discrete pixels in it. Where if you take a vector font, it doesn't matter how much you blow up that vector font, it'll continue to look smooth and continuous. Now, to be fair, this is done on a computer, which is a continuous system, but this is a good analogy of what a continuous system is. It means it doesn't matter how much you blow it up, you will never, ever, ever see an underlying corpuscular system. Now, in the vector system, you will, because there is a limit to the vector system, but this is just a good analogy. So does this mean that a continuous system is infinitely divisible, or is it indivisible? We're actually, this discussion for another video slide shouldn't actually be here, because I actually ended up continuing this discussion in this video. So we're not going to continue this slide, we're just going to continue on. So what are some examples of continuous systems? Well, electricity was once thought to be a continuous fluid before the discrete nature of matter was discovered in the early 1900s. And if you've seen my foundation series, you see we have a little bit of disconnect between Maxwell and today's world that lead to a little bit of problems. So I'm not going to cover that here. But the only example of a continuous system is continuous mathematics. Here we have a number line, and in this number line, there are infinite number of values between any number on this number line. Like, for example, between 3 and 4 would be the number pi. And pi is what's known as an irrational number. In other words, there's no two numbers you could divide, no two whole numbers that you could divide that could give you the value pi. I don't even think there's irrational, but I don't know that part. But so on this number system, is both rational and irrational numbers. And in between each set of numbers, there's infinite number of numbers between you. You could divide between 1 and 2, you could divide that area up into infinite number of numbers can exist there, including irrational numbers. So let's do an example of comparison. Let's take a discrete deck of cards. A discrete deck of cards, there's a finite number of cards, which is 52. And each card can be only of a finite value. It's either ace through king, and it can only have certain number of suits, which are hearts, clubs, spades, and diamonds. Okay, and so you can pull any card out of here, and it's going to be any one of these, any combination of number and suit, and nothing else. Nothing else. Well, I suppose there could be jokers in there, but let's not consider the jokers in the other cards, because it looks like there's a joker right here or something, whatever that is. But if you had a continuous deck of cards, well, theoretically, there would be infinite number of cards. In other words, from the other deck, you could pull the 3 of clubs out, but from this deck, can you pull the pie of clubs out? I mean, you'd have a pie of clubs. I should have put a little extra amount of the thing here, but you'd have the 3.14159, which goes on for infinite digits of clubs. The pie of clubs would have to exist if you had a continuous deck of cards. And we're just going to represent the pie of clubs with this guy here. And what of the suits? I mean, if this deck is continuous, I mean, what's halfway between a spade and a heart? A spark? I don't know. So in theory, you could have continuous suits as well as continuous numbers. And theoretically, then there would be infinite number of cards in this deck. Okay, and so would it even be possible to pick the pie of clubs? And we're going to come back to that. So let's just use probability theory. Let's go to it from a discrete deck. If you were to shuffle the deck and pull out a card, the probability of you pulling out the 3 of clubs would be 1 in 52, which works out to a fraction like this. But if you had a continuous deck of cards that had infinite number of cards and infinite number of suits, the odds of you pulling out the pie of clubs, okay, would be 0. 0. Okay, now I'm about to say something that's going to twist and twerk mathematicians the wrong way, but just listen on. I will come back and put it in a sane way to you. So what we're finding out from this is that probability theory is useless on continuous systems. Now just hold on. Okay, the workaround that mathematicians and engineers use to utilize discrete systems with probability is a system called discretization. And so what we would do with a continuous deck of cards, if one existed, we would say the probability of obtaining a card that is between 2.5 of clubs and 3.5 of clubs, let's assume the suits are discrete, would be 1 in 52. Okay, so we can discretize a continuous system to make it useful. And we do this all the time with continuous distribution. Here's the bell curve or the normal curve or the normal distribution, whatever the terminology you want to use. Okay, and we don't say what's the probability of hitting exactly this value here. We say, oh, well, you know, a standard deviation, in one standard deviation, all of your samples should fit, 68% of your samples should fit within one standard deviation. And so we discretize this to make it useful. We discretize it in terms of standard deviations in order to make this useful. Because talking about any single element on this chart is of no value. And therefore, we can only use a continuous system if we discretize it using probability, I'm saying. So returning to the pie of clubs. So if it were possible to pull the pie of clubs from a continuous deck, it would mean the deck is discrete and not continuous. And you say, why do I say that? Okay, just as the probability of pulling the pie of clubs from a deck is 0, the mere fact that infinite cards exist between 2 and 3 means that the cards can't be made of anything that takes up space, because it would occupy the entire universe. which means a continuous system cannot exist. Now, there's one possible system I came up with. Maybe you can come up with another, but we're going to talk about this one possible system a little bit later. Okay, so the rest of the slides I'm going to talk about are basically except for this one possible system. So everything that exists in the universe that takes up space can only be constructed from discrete constructs that in themselves can only exist in a discrete and limited number of states. Therefore, only rational quantities can exist in the universe, with the one possible exception that will be discussed. So irrational quantities can only exist as close approximation constructed from discrete, otherwise known as rational quantities. In other words, in the universe, you cannot have any irrational quantities. What you'll have instead are the closest rational number for that system. Well, actually, it's going to be the most closest discrete system. But anyway, now I know that there's going to be some imbecile out there who's going to employ retarded logic to say that, well, if pi is a rational number and you don't believe in rational numbers, then you must not believe in circles. No. I stand by what I said. Only discrete approximations to circles can exist. Okay, and if you still want to say I'm full of shit, then show me a measuring device that can measure irrational quantities. Go ahead, try it. Okay, the only exception to that there can be no irrational or continuous systems in the universe is the exception of empty space. Because if I take an object that's at 2 on a ruler and I move it to 4, well, it's going to be passing through 3.14159. It's going to be passing through pi at some time. It's got to pass through it. And so possibly only empty space is continuous. That's the only exception to the rule I will accept, except for the fact that right now we really don't care. It could very well be the case that the locations that an object can exist in space are discrete. However, the fineness, in other words, how tiny the discrete steps are, that's the fineness, would necessarily be smaller than any instrument that could be built to measure it. Because anything built with normal matter is going to be discrete and corpuscular. And those discrete corpuscularity, I am sure, would be much, much, much larger than the fineness of free space if free space did, in fact, have a fineness and discreteness about it. So for all practical purposes, okay, we may never know if empty space is discrete or continuous. However, as long as the fineness of the modeling techniques treat empty space with much more fineness, in other words, smaller levels of discreteness, smaller steps, than the things that occupy it, then it doesn't matter if we model empty space using continuous mathematics or discrete computer models. Okay, again, I'm going to say it a different way. As long as our modeling techniques use a fineness for empty space that's finer than the modeling of the corpuscular matter that's in it, then it really doesn't matter whether empty space is continuous or discrete. And I don't think we're going to be able to build anything with normal matter that would be able to prove if empty space were continuous or discrete. So at this point in the research and the footprint of humanity, this question has to be put off to probably 100 generations from now, when humans can build such machines and measuring instruments to be able to look at things of that fineness of scale. That's far beyond anything we're going to be able to do. But for our purposes, treating empty space as, with finer, because with computer models, with computer models, the fineness of space is going to be discrete. Okay, but as long as we use much more discreteness than we use for modeling matter, then we're good to go. Now, the importance of this definition, there's two important uses coming up for this definition. Okay, this definition is used for the upcoming 14th rule of acquisition, which is called the insanity tale, which makes the argument that nature must be sane and rational. And any theory or model that attributes insanity or irrationality to nature is got to be wrong. The 14th rule of acquisition is then used as a coup de grace quantum mechanics in a following trailer video. And number 2, and this definition is used to support a discrete corpuscular ether model in the electrogravity paper. I know there are those who genuinely believe or want to believe that ether that fills empty space must be a continuous fluid. Well, this video shows that anything that occupies space cannot be continuous. Or it doesn't really matter. As long as our modeling is fine enough, we can model a continuous fluid as a system of particles. Either way, it really doesn't matter to us. When it comes down to it, our computers are going to do things in a very fine, discrete way. And so we've got to be able to, and there are other examples out there that we can use a discrete modeling. As long as the fineness of the steps are small enough, we can approximate a continuous system with good fidelity. So it really doesn't matter. Thank you. No more voodoo physics. And the Distinti site is up, but it's still not finished. Please, do all the things. Subscribe, become a Patreon member, blah, blah, blah. Help this out. The quicker I can do this, the quicker we can get to the promised land of faster than light starship travel, or to the point, prove that, in fact, that the Einstein monkey was right, that you can't go faster than the speed of light. I do not believe that. Physicists have never been right whenever they said something was impossible. That's a historical fact.